So in this video, we're just going to briefly introduce vectors in three-dimensional space. So in the previous homework assignment, the one that you just did, or the one that's due today, I suppose, we looked at vectors in two-dimensional space, or R2. Today we're working in three-dimensional space, or R3. And in two-dimensional space, we had vectors with an x and the y component. So things are just going to analog up a single dimension in the way that you would expect them to. So in three-dimensional space, instead of having two components, v sub 1 and v sub 2, we have a third component for the z-axis. We get a v sub 3. In two-dimensional space, we had our standard unit vectors, I and j, and I was equal to 1, 0, j was equal to 0, 1, and what we saw in the previous homework is that if we had the standard unit vectors, I and j, we could write any vector we wanted as a linear combination using I and j by taking the v sub I component times I plus the v sub 2 component times j, and that this would be equivalent to the vector v that we started with. So in three-dimensional space, all we're going to do is wind up throwing in a z component. So now I is going to be 1, 0, 0. There will also be 0 in the z direction. J will be 0, 1, but we'll tack on a 0 in the z direction. And we'll add in a third standard unit vector, k, 0, 0, x and y are 0, but z is equal to 1. So that's going to give us vectors I, j, and k lying on the x, y, and z axes like you see in the picture here. And then any vector we want, v sub I, v sub 2, v sub 3, we can write it as a linear combination of I, j, k in the same way that we did in two-dimensional space. And then, the key to think about is if, what would happen in n-dimensional space? Well, we would just take these concepts, these ideas, and extend them into n-dimensional space. In two-dimensional space, we had two standard unit vectors. In three-dimensional space, we had three standard unit vectors. In n-dimensional space, we would have n standard unit vectors. In two-dimensional space, our vectors have two components. In three-dimensional space, they have three components. In n-dimensional space, they would have n components. In three-dimensional space, we saw that we had a three-dimensional analog of the Pythagorean theorem. In n-dimensional space, we would have an n-dimensional analog of the Pythagorean theorem. We would have an n-dimensional sphere, which we would call a hypersphere, etc. So the things that we're learning here for 2 and 3 space, they generalize to n-dimensional space. So in the previous homework, we looked at vector properties in 2-dimensional space. Well, all of those properties that were in the previous videos and in the previous homework are still going to hold. We have all of the same properties. In the previous homework, though, we just gave two components because we were working in R2, or two-dimensional space. So for each of these, all we're going to do is add in that third vector component. And then everything is going to work the same way that it did in two-dimensional space. Component form of a vector. Take the differences between, now we need to add z sub 2 minus z sub 1. You want the magnitude of the vector in two-dimensional space. It was the sum of the squares of the vector components. It's still going to be the sum of the squares of the vector components using the three-dimensional analog of the Pythagorean theorem. A unit vector is still going to be 1 divided by the length, but now you've got a third component, and the length is going to have a third component in the calculation. So all of the properties that we learn, they generalize to three-dimensional space, and they're going to generalize to n-dimensional space.